Hi everyone. I hope you can hear me. Okay. Hi everyone. My name is Samuel. I work at Epsilon, and today I will be presenting this workshop, optimizing performance in Shiny, tips and best practices. Uh, I have two screens. On one screen I have the chat, and on the other screen I have the presentation and the whole material. So I will not be taking a close look at the chat, but we will have some sections, and between sections I will be taking a look. Some people are helping me with questions, writing down questions they see in the chat. So if you have any question at any point, please, you can use the chat. I might not answer immediately, but you will get an answer. All right. First of all, I am really glad that we are here. I welcome you all. I am really surprised that this workshop has really uh, had a lot of registrations. Yes, everything is getting recorded. Uh, and now, well, let's go to the material. I'm really happy to be between a lot of Shiny heads. I do love our Shiny, and I am so glad that I am meeting with so many people that also seem to like it. A lot of times we have like workshops for beginners, but I wanted this to be something like more for an intermediate level. It's not really, we are seeing some advanced topics, uh, but I also think this is most of the time will be useful if you already are working on your Shiny apps and you want to boost your performance, because a lot of the times we come from different disciplines. Uh, we come from different disciplines, and we might not have all the software engineering knowledge at our disposal when we start using Shiny. So it is good to have, just some tips, some quick wins we can introduce to our apps to make it uh, somehow faster. All right. Okay. So let's start. Please, before we go to the material, you can use the chat to share who are you, share your name. We can see your name. You all have labels. Where are you from? What time is it there? So everyone knows. Well, I know we are more than 300 people here, almost 400. So it will be good to know each other. And what is your background? Really briefly, for example, me, I am a political scientist. Then became a R-Shiny developer at some point on my career. And your favorite niche R package. Not don't tell me dplyr or ggplot. I know we all love those packages, but maybe something more niche. Like for example, I do love the POR package. That is lower level. Is really present in the tidyverse. Is one of the libraries you load when you do library tidyverse. And I love it. I use it so much. Some colleagues tell me that I use it too much, but I do love it for programming. It's very handy. It's very useful. So you can start sharing those kind of things on the chat, and I will start with the material while we all know each other. Okay. So first thing, this will be focused on performance, and I will try to give you some tips and best practices you can introduce right away on your apps. Some of these will be just really, really quick wins, quick changes you can make, really small changes that will immediately boost performance of your app. Some of these are more focused on kind of strategies you can have for understanding how the Shiny framework works on itself. The server browser communication. Basically, that think of this as a high level overview of different strategies you can apply to boost performance in your apps. All right. Okay. On this link, you have access to the material. I hope I can. I can share this on the chat. So if you see this in there, this is the material. In the same GitHub repository, you will get a link to the slides. If not, I can also share link to the slides. This slide were done using Quarto, by the way. They can use some better styling, but I hope the material is productive enough for you. And this will be the structure of this workshop. We are already doing the introduction. We are using this optimization cycle as a high-level understanding the process we should use when we are trying to optimize our apps. This process doesn't come from me. This exists in the Shiny documentation. This exists in the Mastering Shiny book. So again, this is a high-level overview of many resources scattered across the web that with some expertise, some experience, I managed to collect, and I plan to share with you. Okay, so basically we will do some benchmarking. I will explain what benchmarking means, and we will just do a little small exercise on this. Then we will do profiling, and then we will only at that point we will get to the actual optimization strategies and tips. At the end, I would like to have some space for advanced topics, but we might sacrifice this if we have a lot of questions, or basically these are some other things I would like to share that are outside of Shiny itself, and I'm having some bandwidth, some time bandwidth for the Q&A in case there is. So hopefully the 3 hours are enough for this whole collection of information. All right. Again, some introductions. I work at Epsilon. I hopefully by now you already know what Epsilon is. It's a software development company focused on with a strong knowledge of our Shiny. The Epsilon company make its growth by using our Shiny, now using Shiny for Python and other data analysis, business intelligence tools right now. And Epsilon is constantly on the look for new talent, so you can check Epsilon's webpage and you can find maybe some good opportunities for you. I hope also this workshop will, if any of you is planning to to be hired at Epsilon, it will be good for you to have this knowledge, because some of these are really baseline that we expect people who join us to have. So hopefully this workshop will be useful also in that sense. As I was saying, I'm a political scientist, and now I work as an R-Shiny developer. I am from Lima, Peru, South America. And these are my contact, my webs and everything. If you want to, follow me, I honestly don't post a lot of stuff, but when I do some workshops, I will be posting on here. GitHub I do use a lot. It's kind of my go-to web, because I do use it a lot for work and also for fun. So yeah, maybe in GitHub I will be more present than in the other resources. Okay, hopefully you already did that. I was taking a look at the chat. I know some of you are already sharing this. So thank you for that. Okay, so let's get to the meat of the presentation. I will start talking about the optimization cycle. But first things first, we need to understand what is a computer. Maybe I will. Okay, I guess this makes a little bigger. So when we talk about a computer, we are basically talking about the interaction of three main components, right? And when you are thinking of buying a new computer, hopefully these are the specs you will be looking for, right? The CPU, the RAM, and the storage. Uh, you will be looking at how fast is your CPU. The CPU will be like a huge chunk of the price of your computer, right? Then you will have the RAM. How much RAM do you need? I guess the minimum nowadays is like 8 GB, right? Uh, and then you will be looking at the disk also for its speed, but also for its capacity, right? And these are the three main components we think of when comparing computers, right? Uh, so it's important to have this in mind. We also have GPUs right now that are very useful for things like matrix computations, graphics, etc. But at the core, like the GPU is like a specialized processor, right? This is why I'm not including it here. We have other types of processors also in computers, but these are the three main elements that we need to focus on. And this serves for us to think about computers on two axes, all right? Let's think about time, which will mostly be dependent of the CPU time. How fast is your CPU? Let's also think about space, right? Which will be determined by both your memory, which is RAM, and your storage. Difference between these two is that memory, the RAM is temporal. Anything you have in your RAM will last only for the duration of your session in your computer. So whenever turn off your computer, whatever was in the RAM disappears, right? But we also want computers to store things permanently, and for that we have the disk, the storage, long-term storage. Uh, but there is a hidden axis here, a third axis, which is honestly money, uh, because one you can have faster and you can have bigger storage, but it will increase the price of your computer. So these are like two primary axes, which are time and space when we think of performance and optimization. But there is a hidden axis, which is money. Sometimes some people are okay burning some money. They can. I mean, money is not a limitation for some people. For some other people, it will really, you will only get access to certain CPUs, to certain memory. So this is something we need to have in mind, because a lot of times when we are thinking of developing our apps, we maybe are using a good computer, right? But our clients, our users might be using very old computers, and performance will take a hit when you have to wait for their computer to give you a response, all right? Uh, so have these three axes in mind. Mostly time. Time will be very important here, but storage is also important. And a lot of times, when you have to save, when you want to save some time, you will have to spend more storage. Uh, that is the idea I want you to have present here. You can have an exchange between these two axes. So what is optimization then? Well, it will depend on your needs. As I was saying, here there is a screenshot of my computer, the computer I'm using right now, and you can see that we have a CPU with some speed, we have memory with some capacity, and we have also disk, and it's telling me how much I am using of the disk. Uh, so as you can see, CPU, the most important thing to show in the task manager, they decided to show us the speed of the CPU. All right, so have this in mind. But for the others, they decided to show the storage, and this is basically because this is what matters for each one of those. All right, and I told you money is a hidden factor because sometimes people, I mean, it will limit what kind of machine you can get access to. Okay, having this in mind, optimization, well, basically, I'm trying to say that optimization is you cannot just think of optimization in as some vague term. It will have, you will need to have some real world implication for what you want to optimize. Sometimes will be time, sometimes will be space. All right, but on any given case, you will want to use this cycle. First thing you want to do is benchmarking. Then you want to profile. Then you want to estimate, which is basically part of experimentation. And last part is actually optimizing, which is basically making a decision. In your experiments, you will find some things work better, work faster, but use maybe more memory. But at the end, you will have to make a decision, or maybe the decision will be just to leave it as it is. Okay. As you can see, I try to add some links for whatever resource I am using. If there is no link, basically you will have to take out the documentation of the functions you see on the page. But I think other than that, I try to add some reference. So at each stage of the cycle, there is some key question we want to answer, right? When we do benchmarking, we want to know if it performs as we expect it to perform. Uh, Sometimes you will do your own benchmarking. You will be maybe comparing different implementation of the same thing, and you will be measuring how long does it take. Sometimes you will need to simulate real usage. But benchmarking, can have different, let's say, ways of working. But at the end, the question is, will it perform as I want it to perform? Basically that. So for profiling is basically where are the bottlenecks? Where is the slow part of my computation? Where is that non-performant part of my computation, right? Because when you profile, you will see what are like the biggest wins you can achieve, where you should point your money to or your resources to make it faster, to make it better. Then you will work on estimation or recommendation, and here you will need to investigate, to research what are your options, what can you do to make it better. And at the end, you will have to make a decision and implement. All right. So hopefully you will see this whole cycle during this presentation. So now talking directly about benchmarking, there is manual benchmarking, let's say, and there is advanced benchmarking. For this benchmarking, I'm basically referring to as trying the app and see how it performs. Okay, we are not focusing here on particular functions. We are focusing here on the full app. And I'm just showing you two options here, which is manual and advanced. Manual, you run the app, you try different inputs, you see how it renders, how long does it take, basically this. But there is also advanced options like Shiny Load Test that will simulate the amount of users you wanted to simulate and see how well the app performs, when does it take a hit and something like that. For this presentation, I will not be showing you Shiny load test. I think this is a fairly advanced topic. You need to have, because you need basically to build a system where you can use this kind of software. And this is fairly advanced. I think you will need a workshop on itself to talk about this Shiny load test. But we understand manual benchmarking, and we will do it. So this is the mock-up we will be using for this workshop. When I designed this workshop, I had in mind like 10 people, but we are like 5x the quantity that I had in mind. So this will mostly be done in the webinar fashion instead of me waiting for you to answer my question of I will not be able to wait for everyone to try the things I'm showing. So hopefully that's okay. Okay, what do we have in this app? You can see here we have 3 plots. At the bottom we have one table, and we have some filters, right? We have some data in the backend, and whenever we choose a filter, it will update both the tables, and with this information, it will update whatever we have in the plots. Okay, fairly basic application. I know at some point maybe we all have done some application like this, right? Hopefully at this point in your career, with your knowledge of Shiny, you might understand, you might have an intuition of how the UI and the server will look like for this application. But also, you have, sorry, I did share the link to the material. If you just clone this material and run whatever is in app.r, you will get this application. All right. So I already have this here. I am in the main branch. All right. So let's take a look at the code. All right. But sorry, maybe we can do this while you do this benchmarking. All right. So I have this deployed in a POSIT Connect Cloud service, which is free for now. I am posting the link in the chat. Hopefully you can see it. I don't know if there is a way to... Okay, if you have the link to the... I see the material is pinned in the chat. If you have a link to the material, you will be here. All right. Here you have the link to the slides. And in slide, which number is it? Sorry, I don't know which number of... sorry, it's line 16. You have the link of this application, and is this one right here. Sorry. Okay, I see that you already tried it, and this already broke. That was kind of expected because we have some very limited amount of RAM here. I guess for everyone, for 500 people, yeah, it will be it will break. But you can clone the material, as I was saying, and we can just do run up. So here you will see the same thing you will get at the platform. All right. So you can see here we have 2 filters. This takes some time to load. We have the table here. Maybe I will increase the font size a little bit. All right. You can see, well, the resizing affects the plots here. All right. So let's say I would like, okay, hopefully you can see this app is kind of slow, even though we have some very limited data that we are using here. Yeah. All right. First, so we will not be able to do the benchmark. I mean the interactive benchmark, but hopefully you can see this app is kind of slow. Let's select a new region. You can see the table blanks out, the plots start to load again. Yeah, and if we change the maximum age, sorry, I guess I forgot to translate these labels. This is region and this is maximum age for the people. This is based on a survey. So yeah, hopefully you can see this app. I mean, for one user, it's okay to wait, but when we start scaling, when we add 5 or 10 users of 500, yeah, it becomes a problem because, as you can see, it breaks, right? Okay, so I will show you the code here because we do need to get familiar with the code we're using for this app. Zoom is not working. What is happening? First time in my life I'm using this menu here. Okay, so let's take a look. We are using Shiny and BSLib, pretty standard application. Then we are using a sidebar page, and you can see this in the layout of the app. This is a sidebar page because we have this sidebar. Okay, this is really slow. Maybe the screen sharing is also contributing to that. Then we have just two inputs, which is one select input and one slider input. But the source of the data is this CSV that we have right here, and we're using for this app right now. We are using just a sample of 5,000 observations. This, I believe, this has the full data set has like 900,000, something like that. So yeah, we are using a really small part here. Then we are using this utility, which is fairly new to Shiny, which is use busy indicators. What this does is, when the reactivity is working, you will see some loading indicators here, right? You see these spinners. Before Shiny 1.9, you will need to use the waiter package. Will be maybe the most easy way to have that. But right now it is these busy indicators, and I don't have to worry about setting up any sliders myself. Okay, now we have the main layout for the app, which is I am using cards. First, one card for the table, which is this one. This whole thing is just one card. Then I am using a column layout for the other three cards. Each one of these holds a plot, and you can see this right here, right? And pay attention to the function we are using for the plots, which is plot output. It will have a correspondent render plot in the server where we are using ggplot to render these plots, right? Okay, talking about the server, right? For rendering the table and for every reactive element here, we are filtering for the selected region and for the selected age, right? So basically, we are using every time a subset of the whole data we have available. So hopefully you can understand what is going on here. And we will focus on some problems with this implementation and how we can address them. Okay. All right. So we already saw that the app was kind of slow. Now we will need to check where is it slow and how can we address that, right? So we have tools for doing profiling in R and the RStudio IDE, which I'm using right now, and maybe you are using too, which is very widely adopted in the R community. These RStudio IDEs have some utility to use the profiling, right? Basically, this is done using the profbis package as engine, as backend for the profiling, right? If you don't have it right now, you can use this function to install it. And the basic way to use this is to, load the package and then enter whatever code we want to profile inside the call to the profbis function. This is if you would like to use it programmatically, right? There is another way of profiling. Okay, so this profiling will focus on showing you how much does the R session take to compute whatever value you're trying to compute, whatever function, whatever logic you're trying to compute on the R side, all right? There is another tool which is called ShinyTikTok, which is made by Epsilon, the Epsilon team. This is actually JavaScript that you can add to your application, and it will give you some summaries for how long does it take from the client perspective. Why is this important? Sometimes when you are using just the R side, one implementation, one optimization technique involves using async functionality. For example, promises, right? And something characteristic about a promise is that it computes immediately. So if you try to profile using a promise, you will get nonsense results, right? Even though your promise doesn't, I mean, it's not like it computes immediately. It returns control to the session immediately, but maybe it does the computation elsewhere. And this is why the main R session will not see the time it's taking for it to compute, right? But if you measure on the client side, yeah, it will tell you how long it took for the browser to get the information it wanted. So it's good to have these both tools in mind when you are trying to profile. All right. Okay, so if you have ShinyTikTok, you will run this in the JavaScript console. Where is the JavaScript console, you might say? Okay, let's say we are here. You can use these developer tools that we have in Google Chrome, and any Chrome-based browser will have this. And you will go to more tools here and developer tools. And it also has a shortcut, a keyboard shortcut, if you want to go directly. And what is the JavaScript console? Is this one right here. So when you have an application with Shiny TikTok, you will use this JavaScript console with, sorry, where is it? With these commands, and it will get you the information you want. We will do an. I would like you to focus now on how we will do it on the R side with RStudio, right? Which is for Shiny application is fairly easy to do. So first thing we want to do is to locate the profile menu, and it's very simple, very straightforward. You will have this star profiling option here, and you will notice a really small change on the IDE once you click this start profiling, which is on your R console. You will see this timer, and you will see this button to stop the profiling. All right, so let's do that. I will stop my app. Just to be safe, I will restart my R session. Okay, I always recommend to start from a fresh R session when you try to run any tool. And now we will locate the profile menu, and we will start the profiling. Okay, as you can see, we have this profiling here. Nothing shows in the console. RStudio has some implementation to, let's say, hide this from the RStudio user. But once you clicked start profiling, it started a timer. All right, and this is important because the timer will not stop measuring until you click this stop profiling. So right now we didn't run any code, so it will tell me that maybe some error. Okay, I hopefully the RStudio team can improve this because it's not very communicative, right? But we will use it for actual code, so we will see results right now. So okay, once we start profiling, we can run the app. How do we run the app? Well, we have this big button here, right? Another way is just you source this line by line. I mean, whatever you choose to run the app. Okay, so let's do it again. Restarting our session. Start profiling. Now I will run my app. You can see the console works as always. Where is my app? Should be here. Okay, it just starting right now. Okay, here it is. All right, let's, okay, I see it is triggering reactivity again, maybe because of a resized window. Let's change this to, okay, let's say PCARD. All right, let's now try, okay, let's now try some age here. And this is just very basic profiling, right? Because we only have two inputs, we have very limited amount of outputs here too. So I will now go to RStudio and stop the profiling. So we get now some new tab in our RStudio source panel, and I will explain to you how you should read this tab, okay? Because maybe it's not very obvious. It wasn't obvious for me, at least, when I first saw it. Okay, so we have this profile tab. And the upper section, we have two sections here. You can see we have a section with the code and a lower section, a bottom section with something called a flame graph. This indicates the time required for each operation, right? So let's take a closer look. Here we have the code. We have some columns that tells us the memory and time used for specific regions. This will be mostly important for the server because the server is in charge of doing the computations, right? And you can see which portions of the code use most memory and time, right? And you can see this here. Hopefully this shows you can understand that this histogram is taking longer than this table to render. Okay. Basically, hopefully you can see that, and you can see this by each output. But if we want to have like a timeline of computations, this is how it looks like. Okay, this starts from the zero. The zero will represent the moment we make a click on start profiling, and it didn't start measuring right away. The computation didn't start to happen right away because there were some seconds between the time we did click here and the time we did click on this run up button. Once we start that run up, you can see the bottom here is every code that run here originated with this run up call. So if you are not aware, when you click this run up, you are basically just saying to RStudio to send this command to the R console. And you might remember that we never did send manually this command. This is basically all this button does, if you were not aware. So this started happening, and it didn't stop until we did stop the profiling. Okay, so in this case, we stopped the profiling before we stop the application. But if we will have stopped the application before, this run up will have ended before this axis was empty. All right. So what else can we see here? There is when you call run up, there are lower level functions that are run for you. So this run up is basically a wrapper around several functions that will make the app run. Okay. Also, you can see here these functions read CSV and slice sample, which are the setup for our app. If you can remember, this setup is right here. Here you can see those functions. As you can see, it takes a good amount of time to start the application, right? After that, if we focus here, you can see that I'm doing a zoom in on these sections, where it will show you which output generated the code to run. Okay, so first it ran the output table, then the output histogram, the output by transport, and the output by time, and it did it in that order. And if you see this server, it's basically the same order we have here on the server. All right. Of course, there are some these output render functions are a wrapper inside of render logic that we have right here. If we zoom at the exact place, we will get the actual code. I mean, these pieces of code that we are running in there. So this is called a flame graph because if you look at it like that, you can see that, okay, it will show you the whole list of operations that were performed during the run of this code. Basically, you you see here several sections, because this is when the app started, but this is when the first inputs, the first outputs were rendered, and each time we updated an input, the whole render functions, the whole set of render functions run again, right? So these are those times. As you can see, these are just same thing of these render functions that run. So this is how you understand the flame graph itself, but we also have a different tab. We have the frame graph tab and we have the data tab in the profiler. And the data tab will basically show you a summary of the higher level functions or higher level logic that run when you did the profiling. Okay. So right here you can see the same thing we just saw on the flame graph, which is the main function that we run was the run up. It will show you here something a little bit misleading in this section here, because this is actually the whole time the profiler run. It's not really the whole time the run up function was active. Or sorry, no, I'm mistaken. This is actually the whole time the run up function was alive. The Shiny function was alive inside the profiler, but basically every time the Shiny app is alive, it is using the R session, but it's not doing computations every time, right? So that R session is busy, meaning you cannot use the R session for other things while you are using the Shiny app. So this is what is showing here. But then the other things, the output is the actual time it took during that session to render each one of these outputs. Okay. This object right here is basically the setup. All right. As you can see, it takes a little bit of time. Yeah, basically, if we want to prioritize in terms of time, we will maybe try to focus first on this setup part of the application. Second part will be these outputs, right? Even the outputs, the plots, and the table. So, okay, this, as you can see, we are now having we now have information on where we should focus our priorities, where we should focus our resources to start optimizing our application. Okay, you have some resources here if you want to have a deeper look into profiling. I saw someone asking about the Shiny load test. Sorry, it was in benchmarking, but if you go to the benchmarking section, you will find the link to how you can implement Shiny load test for benchmarking. All right. So before going deep into optimization, maybe some time for some questions. Okay, I will take a look. I have a Google Doc with the questions. Okay, yeah. First question is about from Joseph Orton. Can anyone point me to a good resource to learn Shiny load test? Okay, I will do that right now. Right here, maybe it wasn't noticeable on the slides, but this is a link to the Shiny load test documentation, and it shows you how you can set up your Shiny load test session, resources, and basically this is the best documentation available for how to do that. All right, you maybe find some articles, but maybe they are old, and documentation of the package itself will be the most up-to-date place to look for information about that. Okay, second question from Joanna Jokyo. Okay, Thank you for that. It was asking me to make the font bigger. I think I did that. For profiling, all right. Okay, same thing, I believe. Bigger font. From Tom Road, we have, if your Shiny app uses a large amount of data and has many menus and other elements, is there a code that can be placed on the server to speed up the app's responsiveness? Well, hopefully this optimization part of the presentation will answer this question. We have a question from Thomas. What are the units and scale for time in the profile near the bar chart? Okay. I believe it will show you here. For time, it is milliseconds, and for memory, it is megabytes. We have another question from Howard. What does As Shiny App object do? Okay, I believe you are referring to this object. Okay, maybe, yeah. Sorry, I don't think I can increase the font size here. Okay, yes, I do. I can. All right. So let's take a look. All right. Well, basically, it is doing some utility functionality to start the app itself. This is lower level implementation of Shiny. We should not really, focus a lot on this one. It's kind of the UI part. You can see here, setting up, loading the libraries, setting up the UI. So this will take a longer time to compute if we have a bigger UI, if we have many Shiny modules in there, if our UI maybe has to wait from some external resources. So basically, this is what this Shiny app object is doing. All right. So from the basis, what is there be defined? Sorry, I don't understand the question, Devasish. Rick Stoner, on the data tab, what do the negative values indicate? Is it RAM consumed? To be honest, I don't fully understand why we will show negative values on the RAM, but if I believe your hypothesis might be correct. Might be the RAM consumed and then released. That sounds reasonable. Okay, from Sebastian, do you know what app or package I can use to profile an app developed in Shiny for Python? Oh, there is a great question. I don't know right away, but I will take that as homework for sure. Okay, and last one for right now from Carlton. Is there a way to look at profiling data for optimizing and cross-reference it with user data? For example, if my users use a specific feature at the same time and this indeed it slows down performance, can I get that from profiling? I maybe for this, if you want to simulate user interaction, you might be able to somehow leverage profiling with Shiny Load Test. But if you want to test it with 2-3 users at the same time, you can just do the same thing we are using, but maybe opening several tabs at the same time and doing, computation on all the tabs at the same time. That will be maybe a workaround for now. Okay. Okay, thank you for those questions. I will come back for the new ones that are appearing later. And thank you also, by the way, a dear colleague of mine, Sasha, is helping with the question. So thank you, Sasha, for your work. Now we will get to the actual reason you came here. Hopefully, profiling makes sense to you. But the meat of this presentation is the tips and best practices, right? Okay. Sorry, I think I went. Okay, let's get to the optimization part. And for optimization, we will have three sections. The first one is I called it related to the data. And for data, we have four options, four strategies we can use to speed up the data part of our application. The first one will be faster options for loading data. I will explain which options we might have. As you can see, for our application, we are using just a plain CSV file. I understand this is widely adopted. CSVs are, every operating system, supports CSVs, but there are new formats that might be faster for that. There might be new packages that read CSVs faster, for example. Second option is use more efficient file formats. CSVs are not the only format available for storing data. We have new formats, and some of these are really, really fast. And for this, I did some benchmarkings, and I will show you comparisons for that. The third option is pre-processed calculations. As you can see in our app, we are doing some filters. If we have a limited amount of potential filtered values, for example, here in our application, let's say for this table, we are filtering for region and for age. So for region, this is a discrete variable, right? We only have a limited amount of regions. We could pre-filter by region, and then instead of filtering on the fly, we will create an object that will have a faster lookup time to get to this filter information. I will show you implementation, don't worry. And well, last option will be use external tools, and in this example, I'm using databases, right? Databases are really powerful. They have several advantages, but they also will maybe require you to learn some new programming language, which is called SQL. Hopefully, a lot of you are aware of the existence of SQL. Hopefully, a lot of you are already using it. Sometimes it's the only way to get data. For our Shiny apps is to somehow use an external database, right? Okay. And of course, you can combine all these strategies. So for loading data faster, this is taking into account that our file format right now is CSV, and we have different options at our disposal in Shiny. In R. We have the data table fread function. We have the broom package with the function of the same name, and we have the reader package. We might have some other. I understand read R has some read CSV in chunks or something like that, if I'm not mistaken, which is really useful if you you want to load your data in batches. But for this example right now, I know a lot of you are using CSVs, so be aware that there are new options in there, not just the base R1, and we will make some comparisons. Okay, this is code you can run, but don't do it right now because it takes some time to run. Okay, so I'm using this micro benchmark package, which will take a key and a function to run, and each one of these. I'm using as title of each implementation the name of the function. All right. So I am using this read.csv, which comes from base R as a baseline, to have a fair comparison with all the other options. And this is also the one we are using right now in our application. Okay, we are comparing loading this personal.csv. As you can see, all the code is reading the same file. So the comparison is fair as possible. And this table that we show here is expressed in milliseconds. So everything is in the same unit. Okay. Hopefully all that makes sense. Now, this benchmarking will show us the minimum. Okay, it will run 100 times for each one. We can specify how many times we want it to run, but 100 times is reasonable as a first benchmark. And from this, it will compute some summary statistics. It will compute the minimum amount of time, of the 100 times it run, which one was the fastest one, all right? Then also the max, which is the total opposite, right? Of the 100 times, how long did it take for the slowest one to run? And, all the center values of this. We have the mean and the median, and we have, the quartiles here. So we will focus on these two, but when you will want to compare for your file is hopefully you will take the other ones into consideration too. And for this, you can see what does it mean is that a lower number is better, right? And it means that it's faster. Lower number is faster. Okay, so let's focus on this. It means that it takes, on average, more than 2 seconds to load this data set, and a median time also takes longer than 2 seconds. You can see that all the other options are faster, but the Broom option is significantly faster than the other ones, right? So if we will try to speed up our time for loading CSVs, there is a clear winner for this particular file. Okay, it might happen that for your particular file, some other function is faster. So don't just slap Broom everywhere. All right. If you want to have a real use case for this benchmarking, you have to use your real data or something resembling your real data. And benchmarking is actually good when you try to do real world comparisons. It's the best way to do benchmarking. Okay. So for this particular data, Broom was faster. Now, second option is to use different data formats. Okay, we already did use CSV, but we have some interesting new options available. So, Parquet files, you have feeder files which are compatible with Python, meaning the same file will be, both Python and R will be able to read the same file. We have this FST format, and we have the RDS, which is native to R. I am including this to have, a wider comparison. And also a lot of times when you are using data that comes from an R package, a lot of times it will be serialized to something very similar to RDS. So if you are thinking of, okay, for my Shiny app, first I will make an R package that will have the data set. We'll take into consideration that loading times will be similar to RDS. Okay. So micro benchmarking again, we are again using read.csv as baseline, and we are using the CSV format. For this, I first created, of course, the other formats. It's not like this exists on a vacuum, right? I did create these other formats based on the first CSV. All right, and I believe you have this available. If not this data set, you have this available on the material also if you want to run the same benchmarks. Okay, so we have the CSV.
we have the FST format, we have the Parquet format, which is you need the arrow package to read this. I believe there is a new or maybe a newer different implementation, micro Parquet, nano Parquet, something like that. New package that also can read Parquet files. And you have this RDS key, which is the RDS file format native from R. Same thing, we run 100 times, and we have the medium and average time it took for each one of those. And benchmarking will be different, might look a little bit different each time you run it, because if we compare these values for the read.csv, these are higher than the ones we got here, right? This is completely normal when you're doing benchmarking, because the state of your system might be slightly different every time you run your benchmarks. So it is okay it is okay for it. It is expected to not have exactly the same values as you did on a previous benchmark. All right, but you still get the idea that it takes longer than 2 seconds to load these files. All right. Then we compare the FST format. Okay, in summary, for all these comparisons, the Parquet file is the fastest one by all comparisons, right? Even the slowest time it takes is, really, really faster in comparison to the average time or even the minimum time it takes for the read.csv. So hopefully this makes you understand that using Parquet is a very good format alternative for you instead of CSVs. And this is because Parquet, it stores the information on a different way. I understand it uses column-wise storage, which is different from the CSV, which tends to be row-wise, right? Each line is a row in the CSV. Parquet does some different serialization of the file. All right. So if we compare this Parquet with this Broom, okay, it also means that Parquet is faster than Broom. If you were thinking of maybe, okay, I will just stay with the CSV. Okay, but have in mind that even the fastest CSV reader is lower than using a Parquet file. All right. Again, this is for this particular data set. For some other data set, that might not be true. All right. So always benchmark with your real data. Okay. Third option will be pre-processing calculations. As I told you before, we are filtering for some values, region, and age. So if we manage to pre-compute these filters, we might get an easier way or a faster way to get the specific subset we want to get. All right. So these are the upsides of pre-processing, which is it will reduce size when pre-filtering. It will when you want to do pre-transforming or aggregating, it will save you some time. And if you are able to use indexes, it will enable for really, really fast searches of your content. And this is basically the concept of caching, which is storing pre-computed values or values you will want to use later in a more fast way. All right. We will have a section about caching here, specifically caching strategies that apply to reactive values. But in general, caching is my favorite strategy for dealing with saving time. All right. If can be challenging, it might not be suitable for all the applications, because if you need real-time calculations on your app, let's say, I don't know, maybe your app is for sports, right? And you need the latest status of a given set of matches that are currently on dispute, right? You cannot cache that because at any point in time, the results of the match could change, right? If they are still on, I mean, the match isn't over. At any point, the score of the match can change. So it doesn't make a lot of sense to use caching here. But let's say if you wanted to compute for previous data, let's say data from the last 30 days, right? Data from last 30 days or last month or last year will not change, right? It is already archived. Basically, this will remain the same data. So in these cases, caching is perfectly valid strategy. Or if you are streaming data, also this is maybe a limitation for use caching. For example, if you are using now a chat completion API like OpenAI or Llama or whichever, each time you request new data, which is when you ask for a new response from this chat completions API, it is expected that it will generate new data and it will come in streaming fashion, right? So the whole information you want to display is not complete until you have the last piece of information. So in that case, it also doesn't make sense to use caching, all right? So it's not for every use case, but for sure, for some specific use cases, I will say majority of use cases, caching is your best friend. Okay, so remember this is what we have in the app.r file right now. We are reading the survey data, and when we want to render this table, we are filtering for region based on the input. And let's say for this specific example, we are not just filtering, we are summarizing, we are getting the average time it takes for this variable, right? Okay, so in this case, we are pre-computing a summary, and we are only using one reactive value. We know beforehand, we know our data set, we know that region has a limited amount of options, right? It's a discrete variable, or a categorical variable if you wish. So it has a limited amount of options available. So what can we do? When we pre-process this data, we can do the following. We can get the survey, we can read the whole data set. Then we can get the unique values for the region, which are the list of available options, but unique without repetitions. And on this regions list, we can iterate a function. And this function will actually pre-compute the summary value we wanted based on basically for each region, right? So at the end, we will get a list, another list. Maybe it's worthy to show how it will look like. Let's say region 1, it will get value, right? Data for region 1. And right, you will get a list like this. So then when you want to get the value for a specific region, so let's say this is my computer, right? This is my list. You will only need to do something like this, right? So it will not recompute any value because the average will already be computed on this list, and it will only read. It will not recompute again. This is highly valuable if our dataset is large enough. Let's say every time we run this summarize function, it will have to take a look at maybe a million rows. It will have to make a summary of a million rows, right? So now you are not doing any summary. You already did this computation beforehand, and here you are only reading the value you already have stored somewhere else. So this is highly. Hopefully you can see how, while this is using time beforehand, I mean, instead of using this time each time the input changes, instead of spending this time each time the input changes, you are just spending it once before the app even starts, and now you have a really fast way of getting these values that you already want. So hopefully you can see here we are iterating on the regions, pre-computing, setting names for this, and we have these values. Since we want this to be an R object, read it easy to read without new, we are not using any dependencies here apart from deployer. So we store this as this values object. We store it as a values RDS. Then this is a script that we run beforehand, but then in the application itself, we only read the values RDS, and we subset for whichever region we are using. So you can see how this render table function doesn't have any filtering or any summarizing anymore. It will just be, I mean, a constant time reading of a pre-computed value. All right. So hopefully this makes sense. Hopefully you can see why this is like my favorite way of saving time for my applications. But of course, it means you need to have maybe more care, some sort of pipeline, automated way of getting these values beforehand. And there are options for that. You have GitHub Actions, you have cron jobs, you have, if you're using Posit Connect, you have schedule reports. I'm sure you have the equivalent of this on any platform you are using. So yeah, this is great. And last way of making this data part faster is using relational databases, which can scale in a whole better way of how we will scale by just using our limited memory. Uh, they are prepared for handling large volumes of data. They are optimized in a way that making a query, or meaning asking some data from it is really fast, and they allow for persistent storage, right? Anything you store on a database, I mean the classic database, you will get stored on a disk somewhere else. So this is really good. If you want to learn SQL, I mean, these are very notable examples of databases, which are SQLite, MySQL, Postgres, and DuckDB. DuckDB is fairly new. It is relational, but it's also column-wise. It has really good implementation for analytics. So take a look at DuckDB. I mean, it's really good. It's really cool. All right. And if you don't know anything about SQL, you wish to learn, there is a free code camp course for beginners, which is really good. I took it myself when I wanted to, increase my knowledge about SQL, and it's really good. I encourage you to try it if you don't know SQL yet. All right. I will, before doing this exercise, I will answer some questions. So, all right. Michael Morales has a question. My app had many elements to update. The problem was not memory or server, but network. I found that using delays helped. Is there a way to measure it efficiently or formally? You will need to use benchmarking strategies. You will need to use Shiny Log Test or one of the profiling tools I was showing you. If you want to measure, if you want to include network in the, in the picture here, Shiny TikTok, which is in the profiling section, is a good tool for you to add to your applications. Yeah, basically, I will tell you, Shiny TikTok might be the fastest way for you to have some measurement of how long does it take for your application. Shiny TikTok example. I'm sorry. I wish we would have some time for that, but we have a lot of material we need to cover, so there is no time for a Shiny TikTok example right now. But if you go to the repository, you will have some documentation here. Hopefully, it is helpful for you. This was a question from Emily. We have a question from Michael Osipovich. Why do I recommend restarting the session before profiling? I basically recommend restarting the session before doing anything because it allows you, depending on your configuration for RStudio, it allows you to have a blank state for your R session. Basically, this is the reason. There was a talk from Jenny Bryant, some then called RStudioConf, now PositConf. I believe it was 2018, which was where she explained it, why it is a good idea to restart your session and to never store data, persistent data about your R sessions. I encourage you to look for it. So also we have Svetlana Freiberga. Can it be used if I have my Shiny application in Golem structure with multiple modules? I not sure what you are referring to. I guess it was about profiling, and yes, if you are using Golem, profiling is will be the same idea. You start the profiler, you will run your Golem application as you will normally run. Maybe you will need to install it first. I don't remember how Golem applications start. I believe you can install the app, the package, and you will have a utility function to run the application. So maybe that will be the best way if you are trying to use profiling with Golem. Next, can you profile already deployed app in Connect? Not with ProfBiz or RStudio, but you can use Shiny TikTok because Shiny TikTok is a JavaScript, script, right? So if you add it to all the other JavaScript you have for your application, it will be present in Connect or on any platform the user will be, accessing your app in. So you will not be able to, to have a profiling tool in Connect. That's ProfBiz, but you can leverage functionality from Shiny TikTok. But you will need to do it for basically every user, right? Then, does this R package take care of Shiny app working with databases in the background like Mongo? I believe you are talking about ProfBiz again. It doesn't take care of the application, of the database itself, but if you are using some functionality to read information from your database, it will include how long it takes to connect to the database, to pull information from the database. Yes, whatever it takes time to do in the R session, it will include in its computation. For the optimization data section, we have question from Joseph Orton. What are ways to speed up your processing when you are already using DBs and SQL? For this, you will need basically to optimize your SQL queries, I believe. Maybe you are using something like dbplayer. I will say oftentimes when your queries are simple enough, it will give you a good query. And then DB Player is an interface for you to not write SQL, right? But if you are using SQL itself, you might need to manually, optimize your queries. There are tools depending on your SQL engine. There are tools. Each SQL engine will have a tool which will be very similar to Profiler that will tell you how long does it take for each particular part of your query to run. So I encourage you to look for that. Okay, Philip Probst, do you prefer fast FST format, DuckDB, or some other file format for fast loading of only parts of the data? This is a good question. If you want just a section of the data, I think databases might be the best way to do this. DuckDB is for sure a good way to do it. I understand maybe the Nano Parquet package. I believe the author is trying to implement a way to read just a subset of the Parquet file. I'm not sure that it is supported for any other of the formats I showed you here. But databases such as DuckDB, MySQL, Postgres are good options for reading only parts of the data. This is a good question. Sebastian Narvaez asks, is it secure to include SQL code to query data in a Shiny app? Because it is not a recommended practice for developing web apps. What do you think about implementing things like APIs to manage data for Shiny apps? It will depend on your use case. I generally think, and I do myself implement APIs when I want to work with databases. So the Shiny app itself doesn't connect directly to the database. This is my preferred way of doing things. I understand a lot of frameworks also support this idea, but oftentimes Shiny apps run in isolation. And if you just want, some simple query for your app to start, maybe making an API is an overkill. But if you find yourself doing a lot of SQL queries, yeah, it might be a good idea to start thinking on an API. But I don't think it should be your starting point always. Next question from Dia Basu. If I have a large dataset in SQL DB and I want to retrieve the whole table in my R Shiny app, is there a way to do it faster or avoid from loading into our memory? I do not recommend getting the whole dataset or the whole database. I will not recommend getting the whole database on a single call. I recommend you to look into concept of pagination for databases, which basically will imply using the limit and offset clauses or in your SQL engine. So look for that, please. Okay, we have a lot of questions. I'm really glad for the questions, but I will show you some examples of how we can implement this for our example application. And well, basically, and we will need to have a break because this is a lot of content, and maybe some brains are frying right now, including mine. Okay. Okay. Normally, I would like for this to everyone try to implement its own strategy, choosing the right fit for their own data set. But I will have to show you just myself for now. So we have this app.r file, and the only thing we will like to do right now is to change either this function or both this function and this format, right? I don't remember which was the format that was faster. I believe it was Parquet file, right? Okay, so we will use Parquet for this one. I believe we already have this Parquet, okay, Sarby Parquet file. Please remember how long did it take? I don't remember where I should look for how long did it take for it to run. Sorry, no. Okay, but server. Okay, no, sorry, I don't remember where should I look for checking the starting time of the application. But it will be as easy to do this right here. We have arrow and we have read parquet, and instead of .csv, we will have to change the format, right? It is as easy as that to change the way we are loading our data. Of course, for this, before you will have to on a separate session on a separate console to read your survey CSV file and then writing it as a Parquet format. So this will look something like this, right? Data and survey CSV, and you will have to do arrow, right? Parquet, you will have survey on CSV. Okay. So this is all the setup you will need to do if you want to have this file available. All right. It's very simple. As I told you, the goal of this workshop is to give you quick wins. So this may be a quick win for you if you're trying to optimize loading time or starting time of your application. All right. Or maybe you are, reading several files in your app. Okay, maybe it can for each file you will get a faster loading time. All right, we will do a pause here, 10 minutes, 10 minutes please, for you to take some water, take some coffee, and we'll meet you again in 10 minutes. Yes, 10 minutes. Okay, everyone, we are back right now. I will answer some questions that we still have on our backlog. We have one from Eloise Wilson. Hopefully, you are hearing me. Please confirm. If not, we have a question from Eloise Wilson. Can you load data in batches that are based on reactivity? For example, if a user clicks on variable A, it will only load data related to variable A from a database and not load variable BC. Yeah, for sure, you can do that. If you don't write a SQL yourself, the dbplayer package is a strong alternative for simple queries. So yeah, this is actually, I encourage you to try to do it, because this is actually the whole purpose of having a database, to not load the whole data every time. We have new question from Michael. We use dbplayer a lot to convert dbplayer language to SQL. Then we don't need to write SQL ourselves. That is true. Do you know of any alternative ways of interacting with databases without having to write SQL? I am not aware of any alternative right now for R. There is one DM package, is just two letters, DM, which stands for data model, I believe, but offers you similar interface as the one you have for dbplayer, but it's more focused on the data model itself, the relationships, the primary keys, foreign keys, and all that stuff. But we don't have, a strong alternative for object relational mapping for R, other than dbplayer. Okay, we have one from Elodie Chapeau-Blanc. I usually load data directly into our data format. Is it optimal compared to CSV? I cannot answer that right now. You will need to do benchmarking on your actual data set. I encourage you to do benchmarking and compare it to CSV or Parquet or all the other files we are looking in the session. We have one more from Christy Conry. When it comes to best practices, does Epsilon have industry benchmarks around app performance? For example, one output of 100 megabytes should load within X amount of milliseconds. That will depend on the client, I will say, because again, optimizing is not, you don't optimize in a vacuum. You have objectives and you have priorities, right? Maybe even if your app takes long time to load 100 megabytes, maybe the priority is to add a different feature instead of making it more performant. Maybe your priority is to load a wider range of data, or support different file formats. Optimization is not an objective on itself. It exists in the context of whatever you are trying to get from this application. So yeah, it depends. Sadly, that is the answer. From Ali Abdallah, how about the QS format? Well, how about that? I am not really aware of this format. Maybe it is faster. I had to choose some of the available formats for the benchmarking, but you are welcome to do your benchmarking. Please share the results, the comparisons. We have from Tandy Montgomery Xoban. Can you save lists as Parquet? Like, can you save them as RDS? Not sure, to be honest. believe Parquet might have some functionality to save columns of JSON. If not Parquet, maybe I am mistaken for DuckDB. I'm not so sure, but you can always serialize to JSON, save it as a string or character, and then read it and deserialize it. There is a strong option. A lot of database engines do basically that when you try to store, tree-like data, such as JSON. We have another question from Amar Ulwan. What about data format in environments like polars versus data frame versus data table? Again, please, for other formats that were not shown in the presentation, you are welcome to try your benchmarks on your real data set. You will have a better information for doing your own benchmarks. New question from Thomas. Under what circumstances should you rather use RDS versus Parquet, or you say with fast reading for CSV, some golden rules? Well, not really sure. I mean, I do like Parquet for tabular data, but for data that is not tabular, such as lists, sometimes you will have deeply nested lists. And if you want to be sure that the data types you will get from that thing you are saving will be exactly the same as the one you want to read, RDS for R is your best option, because it will serialize something. I mean, the same thing you are writing is the same thing you will be reading afterward. It is not always true for JSON or for YAML, other formats that you could use to store data. So maybe, or some objects that are really complex to store, as for example S3 classes or S7 classes, R6 classes, that are truly deeply tied to the R ecosystem, that maybe these are not the best option. JSON is not the best option for something like that. Okay, so Mosa Diallo says, but if Sorby is an file provided by the user, the pre-processing must happen in the app? Yes, that is correct. If you have, we are using right now static and local data, right? It means that this data will be deployed alongside the application, will be part of the source of the application. But if you have dynamic data, you will need to think of different strategies. And maybe it's worth it to, have some pre-processing when reading the data. And then when the user maybe wants to, if you are using this data for something like dashboard or dynamic plots, it will be faster to generate them dynamically if you did some pre-processing at the start. All right, we have more questions, very good questions, but I will need to continue with remaining sections of the app. Remember, we do have some buffer at the end for more questions, so don't worry. I will try to cover all the questions. If not, what can we do? I don't know. Maybe some questions will be left unanswered, but I will try to take a look at the chat later and try to answer it in there. Okay. Now, for Shiny related optimization, this is basically related to reactivity. All right. Shiny is a very good framework for reactive interactive applications, meaning that your user interacts with some input or some part of your application, and your outputs, your tables, your plots are reactive to that interaction, right? This is the concept of reactivity, and I encourage you deeply, highly encourage you to check the Mastering Shiny book by Hadley Wickham. Is the best resource for you to understand reactivity. There is a section about reactivity graph. Basically, there is no other resource that is better to explain this concept. I'm trying here to make a high overview of the process for the communication between the browser and the R server. Hopefully it is understandable. I will try to make this a little bit bigger because I see, sorry, not possible. Seems that the width is fixed. All right, something like this. No, sorry, not possible. Okay, so but hopefully you can see this in your own screen with the link of the material. But this is what happens when your user interacts with your application. The user will go to the URL wherever it is deployed, even if it's locally. You have a local host based URL, right? And then whenever the user goes to the URL, the R server will start the setup phase of your app, right? Let's say, what can we call setup? Actually, everything here is the setup, all right? Uh, Even reading the data, building your UI, building your server. Server is a function, so it doesn't run until we tell it to run, which is right here. Here is the moment where we are telling the server to start running, right? So that is the setup. I'm marking this step as building the UI, even though it's part of the setup here, because UIs can be really complex. This is a pretty simple UI, but you can have several modules. You can have several tabs on your application. And for this part, I'm only referring to this UI part of building the UI itself, right? Because you also have functionality like UI output or render UI, which is I think is very widely adopted when you want dynamic UI or UI based on user interaction. But this is not the part I'm referring to with this build UI, right? Then you have the render UI, and you can see that this step of building the UI and rendering it, it goes into a step of server browser communication, right? The Shiny framework kind of hides this implementation from us. They are using something called WebSockets, which is a really good standard for browser server communication. But basically, all the UI you generated in your R server will need to be communicated to the browser, and it will be shared using this WebSocket protocol. And then the browser will get this information, and it will be on, let's say, the hands of the browser to render this UI, right? So this is very important to understand, that this step will happen in the browser. So even if you are using Shiny functions that will, let's say, for example, right, you have this Shiny, and let's say you are doing Shiny action button, and you are doing something like, let's say, test ID, and let's say my label, right? This is the minimum requirement for the action button. You see that it generates HTML, right? Uh, Even if this generates HTML, this HTML as a string is communicated to the browser, and the browser will render it to the client, to the user, right? So it's important to understand this step, because once the UI is finally rendered, then reactivity starts. All right. It might have happened to you that you were expecting some initial reactivity when your app is starting and you didn't get it, and this is the why, because it doesn't start until after the UI is rendered, right? And again, I'm not talking about UI output here. I'm talking about the initial UI. So okay. Then, here is the part of the reactivity, and it is a constant communication between the UI and the Shiny server. All right. This is basically a loop until the app until you stop the application. So this is the core of what I will focus on this section. You need to understand reactivity. There is a very interesting workshop that will happen today from Douglas. He will be explaining some deep concepts about reactivity. So I encourage you to join in there. If you have if you feel like you need to understand it better, please do join the Douglas workshop. So okay, this I wanted to give you some context on what we are going to focus on this part. Okay, so on the Shiny side, when we are talking about optimization of reactivity, I will be referring of making the CPU to do as little work as possible. And this will be translated into faster times for your application. All right. Also have in mind that having making the CPU do as little work as possible, it actually means the CPU will be available to do more work, right? Because right now, if you do some work faster, you have more time available to do other work. So it means that your app can have better scalability. It means that one single user or one single render function is not taking the whole available time that you want for your CPU, all right? So optimization allows us to have better scalability. So first thing is we need to reduce somehow the reactivity. All right. And in this example, I have chosen just two of our output functions that we have in our application, but remember we actually have four of them. So for every output function or logic, we have a call to the input region and a call to the input edge. So every time Shiny detects interaction with or changes on these values, on any of these values, it will trigger this logic. So if you only make a change for region, I don't know if this is running, I will make it run again. Okay. All right. So every time you interact with one of these, it will trigger the whole logic, right? Not only here, but also here. So every change in region will trigger all this logic for each of these outputs. On our application, we have four outputs. So every change in region means rerunning the code four times, right? And the same thing, every change on the age will mean rerunning the code sometime. Not just rerunning the code, sorry, is rerunning this filter logic, right? This filtering logic. We might have a way, this looks the same as this, right? We are using the same subset of data. So it will make sense to move this logic to be recycled for each output. So this is what I mean with reducing reactivity, right? It's not this one, it's this one, okay. All right, so let me change this input here. This is very, very slow. As you can see, when I change this, everything changes, which is expected. But if I will happen to change two things at the same time, it will generate a queue of changes, and basically it will take a long time. So what can we do here? Let's focus on these sections that are highlighted. Hopefully it is visible on the screen. these have the same logic, right? So we will only need to create a new object that will hold this logic, so we don't need to rerun these filters for every time, like 8 times, right? So what do? We use reactive, which is kind of the same way of declaring a variable that you will do in your R scripts, but with support for reactivity. Um, in this case, we are moving the filtering logic to be inside a reactive object or a reactive variable. And so this filtering logic will only happen inside this reactive. So instead of happening everywhere, this will happen just inside this reactive. And once this reactive is updated, only then it will trigger a change on the rest of the outputs, right? So even though you can see this filter here, this is not a function. This is a variable, right? But it does listen for change on this variable. So what we are avoiding here is basically filtering at every step. We are just filtering in a single place, right? So this is the easiest way, to start reducing reactivity in your application. Maybe that term is not exact to say that to reduce reactivity, but to recycle logic to reduce CPU usage in your application. But have in mind that creating new objects means that more memory is being consumed. Right? These objects live on the memory on the RAM. So basically, we are making a trade-off between memory and CPU time, and this will be the case. Maybe this is almost always the case that we are having a trade-off between the time axis and the space axis. Okay, as you can see, this filter holds this logic, and then we only refer to this filter when we want to update the rest of the outputs. All right, so reactive is really easy to understand, but we still have uh, our filter value, to react to every change on these inputs, right? As soon as you make a change on these inputs, it will trigger some reaction. And for this example, this is fairly, short time to run, but it might happen that your reactive value is actually comes from a really slow process. It might take you 10 seconds maybe to run, 10 seconds, 1 minute to run. So imagine that for each change here, you will have to wait 10 seconds. And if you want to make another small change, another 10 seconds, and it generates a queue. Now you have 10 users, you have an infinite queue of changes, right? So another useful way of controlling reactivity is actually, start controlling reactivity is to use this function called bind event that will only trigger the reactivity for some specific event. For example, we are creating here a reactive value which holds some slow reactive computation, but it will only start computing this once we use this trigger. Once we change this trigger value, or once we send an event to this trigger value. It works for reactive and it works for the observers in Shiny. Before versions 1.6, I believe, which was introduced 2021, and you will see a lot of code that still uses this observe event or event reactive, which are the same thing. Event reactive is a wrapper for this logic, and observe event is a wrapper for this logic here. So if you see code like this, it means internally Shiny is using this logic here. So for our example, we do need to make some change on our UI because we want to have a new input, which will be an action button, and our reactive value will only be computed once we trigger this action button. So instead of just our select input and our slider input, we now add a new action button. And in our reactive value, we chain or we pipe this bind event functionality. We say to only listen to this event when we want it to be computed. So remember, this input compute is this same input compute that we have here. All right, compute, and we have here compute. So whenever we click on this action button, it will start the reactivity here. We are using this ignore null false just because we want this to run when the app starts. So when the app starts, this button has a null value. So we wanted to say, okay, when it's null, still run this computation. All right. Maybe it might be worth it to show you how it looks like right now. Okay, we have this. I will stop this. We can add this here, action button. I believe we want it to be called compute. And we want the label to be compute. All right, so, okay, I guess we missed that. Reactive, we get this here, right? We do this bind event here for input compute and ignore null false. And now we have this, on this part we only call the filtered reactive variable. Same for here, same for here, same for here. Okay, hopefully this works. You know, live coding is dangerous. I think we have everything. All right. So right now, it is computing based on these initial values, initial filters. Okay. But when we make a change, it no longer triggers reactivity. When we make a change to these inputs, no longer triggers the reactivity. It will only trigger once we click on this button. And you can see only when we clicked, we start seeing the loaders, right? I guess these loading indicators. So again, this will not react to every change in the input. Only we are controlling reactivity by only allowing it to be computed when we click this particular button. So this is very important technique to I mean, even the user will anticipate that, okay, maybe this compute button will something will happen that I will have to wait, right? It's also managing user expectations. Okay, so good technique for you to have in mind. Next one is caching strategies, and this is very important because after, again, Shiny 1.6, we have this bind cache function that is a very easy, straightforward way to add caching logging to our application. It means that you will not be pre-computing whatever values are before your app starts running, but it will detect any computation that happens for this reactive variable, And when it sees the same inputs, instead of recomputing the values, it will read from some cache storage that it will have. All right. So how do we implement this? We only add this bind cache function to the right after the reactive value. So this mostly makes sense for reactive values, but you can also use it directly for render functions, such as render plots, even render UI, even the other one, render texts, whichever other render functions you have available in Shiny. And it is important for you to know that it's better if you explicitly state the variables you want to cache. I mean, you have to explicitly state what the variables that your cache will be based on. And in this case, it will need to be the same variables, the same inputs that you are using inside your logic. Okay? So have this in mind. If caching is not totally working as you expect, meaning, for example, if you forgot to put input age, whatever the age you specify in your app, in your input, when you are using the app, it will return you, if it's for the same region, whatever the age it is, it will always return the same result. So you have to use all the inputs that you are using inside the reactive value. Otherwise, you will get nonsense. And it might be a little bit hard to debug because it will not give you an error. It will just give you wrong information. So yes, there is also a trade-off between how easy it is to use these interfaces for such as caching, and how easy it becomes to mess your app, how harder it becomes to debug. So you have to be really attentive of how you are implementing your caching. There is a say in computer science that the two hardest things for computer scientists is to name variables and to have strong caching. I believe it's cache invalidation is something that is called the technical term. So yes, caching is hard. I mean, slapping bind cache at it is really easy, but it increases the complexity of your application logic. So don't just do it willy-nilly. Be really attentive of how you are implementing it. All right. So, and if you are using bind cache, it's not really mandatory to use also bind event afterwards, right? But I mean, we still want to control the reactivity here, so this is why I am using it. But maybe sometimes bind cache is fine by itself. Okay, so how can I show you this? So basically, I will be here. I will be, between two regions. You can see that this takes some time. Britain takes some time to load everything. And let's take course, and again we compute this, and it takes some time to run everything. Here, every time we click compute, we are starting the computation from scratch. We are recomputing the reactive value. So hopefully you saw that. And now we are going to add here the bind cache, and we are doing input region and input age. All right, both inputs were, I will say, all the reactive values, not because reactives can become from other reactives, right? All the reactive values we are using inside this reactive logic are meant to be keys of our caching storage. All right, so I will rerun this. Okay. Okay. And after that, I will again, we're using retain. Okay. So last time it ran, it created a cache object for our first region in our cache storage, which is right now is invisible for us because it's in memory. There are ways to make it more, visible. But next time we run again these values, it will not recompute again the whole thing, but it will use whatever it was stored in the cache. So maybe it will be visible right now. Retain should be quicker to load. If it's not right now, I will explain why in the next section. I mean, right now the app is really slow, I believe, because of the screen sharing and the network and everything. But I will, in the next section, we will take a look at some other optimization. Okay, so just for you to have in mind, it's really easy to add caching to specific reactives or render functions with this bind cache functionality. By default, it will create, okay, I don't know what's happening here. By default, it will create a cache at the app level. So this cache will be shared for all your users, but you can specify in this as a parameter of bind cache if you want to use a different cache level, right? So right here, if in your bind cache, I mean, the default will be this. These three dots represent whatever inputs you are passing to the cache, and this cache parameter is the cache level that you want to use. By default, this app that will create 200 megabytes cache available for every user that interacts with your app. So have this limit, this size limit in mind too. You can also specify instead of app for the session. So in that case, every user will have its own cache. If I run any computation, other user will not be capable of accessing the cache I used. So this is valuable. This is important when at the user level, your data might be sensitive, right? Maybe you are passing some medical records, or you are passing some, this user is a supervisor of a subset of people, should only have access to some particular data. So in that case, it makes sense to have cache just at the user level, because otherwise the cache will be shared for all users, and some particular input will maybe reveal information that is not meant to be shared with that particular user. So have this in mind. You have different levels of caching. You can also create a custom cache object plus options. And for this, please read the documentation of the Shiny application. Here I have open this, and this is basically the same explanation I'm sharing with you, this reactivity. And for around here, we have this, maybe, right? Right here we have the same functionality. As you can see, I showed you for a reactive, but you can slap the cache right away in a rendering function. It will work just the same. Instead of in caching the reactive, it will cache the actual HTML of that the render is returning. Okay, so something to have in consideration. I mean, this is a new section of the optimization, is the server browser communication. And someone already mentioned before about the network, right? Because application exists deployed in a server, and the server needs to be accessible from the internet, right? And the server will be located on a particular place of the world, right? It doesn't exist on the literal clouds. It exists on a particular server in the world, right? So since you need to send information between browser and server, uh, the size of the information is really important, because if your data is really big, it will take a longer time to reach the browser, or vice versa. If you are using something like file input in Shiny, if the user is loading a big file, it's understandable that it will take a longer time to to reach your server. So it's also important to have this in mind. So basically, larger data means longer sending time. And another factor is the speed of the network, of the connection, right? Because even if you have small data, if the speed is really slow, the connection is really slow, it will also take a longer time to send. So these are also two axes when you need to be aware of when you are thinking about communication with the in browser server communication. This is also important if you are working with databases because the same idea applies. This is why it's sometimes valuable to have some subset of your data, some core data deployed within your app, because since they are on the same server, they don't need this small data will not need to reach any network to be available on your app. But sometimes you do need the only way of getting this data will be from a database or from other services such as Google Drive. I don't know, Amazon S3 buckets maybe. So in that case, the network will be very important, right? Okay. Another thing to consider if is the data is large to be displayed in the browser, it might take a longer time. It might take a longer time to be displayed, right? Because the browser also this works in a computer, which is your computer, the user's computer, and it will depend on this the specs of this computer on how long does it take to render things. And you never know, maybe the user's PC or phone might be a toaster, might just take maybe the user has really bad browser, really old browser version, is not optimized for the kind of data you wanted to send. So all these things you need to have in mind. So what is the bottom line of this is you need to reduce whenever possible the size of the things you are sending through the network. Okay, this is the bottom line. Or you need to reduce the frequency of transmissions, such as using this bind event functionality when you will only transmit reactivity when you click a particular input, such as the action button, right? Reduce frequency, reduce the size, or the same information in smaller parts. This is called server-side processing. It's also called streaming. Also, actually, server-side processing is an implementation of streaming. You will see this if you have some APIs. You might be able to handle this kind of things. I'm not sure that you can do this in Shiny because of the WebSocket protocol Shiny uses. But yeah, these are all the available options you have. For Shiny, we already know how to reduce frequency of transmissions. We will take a look at how to reduce size of some type of transmission, some type of messages that the Shiny server will try to send. For this one, we don't have a way. I'm not aware of a way of doing this from the Shiny itself. Okay, so for reducing transmission size, basically, we want to allow the browser to do some work that otherwise will be done by our Shiny server, right? Uh, this is very evident to do with plots, because for plots, if you are using something like ggplot or the base plot functionality, or I don't know, there is a lattice package, but basically all these packages that will send an image to the browser will hopefully you can understand that images or movies or this kind of media tends to have a larger size than text that you will send. So if you replace your render plot functions for something like plotly output or render plotly, you will instead of sending the image itself, you will send a recipe to the browser to make the plot in the browser side. So in this way, I mean, it's the same as basically as cooking, right? If you want to send something a meal, it might be more expensive than sending someone the recipe on how to make the meal, right? It's the same concept here. We are talking about recipes on that sense. All right. So how we do this, and this is really really easy to do. Some basic plots that you make with the ggplot will only need to be you will only need to replace this output function and this render function. For some plots, this will be all the optimization that you need to do using Plotly. Some you might be using some ggplot extensions. I mean, something like, I don't know, patchwork, something like these things that allow you to put plots side by side. Small plots embedded in the other plots. Okay, those might have you might have to translate your ggplot logic to Plotly logic in a different way. But for a lot of plots, it will be as easy as just slapping this, replacing the output or render function. All right. So you can take a look at the Plotly.js, Plotly.js website. You will have you will have a dedicated section of ggplot, of plots that are supported to be translated from ggplot right away to Plotly. So you will have a whole library of those. And if you want to start from scratch, you will also find the code in there, how you can create, instead of using the ggplot syntax, how you will use Plotly syntax to create the same plots. But again, for a lot of plots, this will not be necessary. There are other similar packages that share the same, idea, that you take your ggplot code and you just change the render function, and you have a browser-based rendering functionality. So these are the list of some of those packages that I know of. Maybe you will know some more. Please feel free to share in the chat. Okay, this is for plots. So let's take a look at how we will implement that. So first thing, we have this plot output here. So for every plot output, I will take Plotly and I will replace with Plotly output. Okay, this will be first step. I believe we only have 3 plots, all right? Then I will go to each plot, and instead of render plot, I will use Plotly, render Plotly. All right. And now when we run the app, you will notice that Plotly will give you some different options here. There are ways to configure Plotly to do whatever you want. Also, when you use Plotly, you will have the resizing will work in a different way as it will work by just using ggplot. Something like this. Instead of going to the R server and making a new plot on this new size, Plotly will just use the browser to re-render the plot, because again, with Plotly, we only share the recipe. So the browser is in charge of resizing and rendering, everything related to rendering the plot itself. So yeah, as you can see that when we resize the plot, we are not getting this loaders that we used to get when we were not using Plotly. So again, this is something really easy technique to improve app performance. Another technique I would like to share with you is server-side processing. This is mostly available for table outputs such as DT. Right now in our application, I believe we have it open here. We are using the basic render table functionality that comes with Shiny. And what it does is it sends the whole table at once to the browser. So if we have like 1,000 rows here, it will serialize those 1,000 rows and will send it to the browser, and the browser will take care of rendering that. But if we instead use something like server-side processing, but which comes by default with a DT package, what it will do is it will only take whatever is necessary. It will only send to the browser whatever is necessary to render a page size. And I mean, this will be more understandable once we see the example, but the change in our application will be basically the same as we did for Plotly. You will locate the output and render function for the table, and you will replace with these ones here. Okay. Another option is using React Table, but for React Table, if we want to use server-side processing, this is available with an extra package, which is reactable.extras, which is made by Epsilon. I understand. I took a look at the React Table repository last year. They were trying to implement some native server-side processing. I don't know if it's finished, but right now it is available with React Table extras. But I will show you the example with DT. Where is our table? Here it is here. Instead of table output, we do DT and DT. Sorry. DT output here, and same thing with our render table, and we have here render DT. All right, so I will show you how DT looks like. As you can see, the table render faster than before, and by default it will give you a search functionality here. It will give you pagination here, for whichever page size you want to have. This means how many rows you want to display at the same time, and you have pagination controls here. You have also information about the total number of rows available, and if you do next, only when you change the page, it will ask the Shiny server for new rows. Okay, it's not sending the whole table at once, but only when you change this page. So since we are sending smaller size data, it is almost it's almost invisible that this right here is a request to our Shiny server, right? But this is just because we are sending smaller data. And if we may change this, you can see how faster it was, just because that before we were sending a really huge table. Right now it is really fast, right? Okay, so again, those are really quick wins that you can implement for your applications if you don't have them already. And many of Shiny applications, which are mostly dashboards, in many cases, will need to display either tables or plots, right? So it's good for you to be aware that there are some table rendering functions and some plot rendering functions that will make it just so much faster, so much easier on your CPU. All right. Okay, for this exercise, we don't need to do it anymore because we already did. And okay, last part of this presentation will be focused on async functionality. I'm not gonna lie, this is kind of a hard topic. So if your brain hurts after hearing about async, it is normal. It is not easy to understand. And again, it will raise the complexity of your application logic. But it can give you some really nice improvements, some really nice scalability at a whole other level than just changing rendering functions or anything. So first thing we need to understand is why do we call it async? And to be honest, I think the name is a bit unfortunate. Full name is asynchronous programming. Use async as with when we abbreviate. But it's a name like this in contrast to synchronous programming. That is basically means when you are doing synchronous programming is that each task, each operation of your program will run sequentially, right? It means the first thing you have in your program will run, and the second thing will not run until you have finished running the first thing, right? And the third thing will be the same with the second thing, and this will be sequential, right? Uh, you might have seen this, you might have experienced this in your normal R scripts. If you are, sourcing an R script, it will run from the top to the bottom, and it makes sense that it runs like that because any value that you create at the top will be available at the bottom, and it makes sense that you will have this sequential thinking, sequential ordering of your operations, right? So when we're thinking about our sessions, this synchronous programming is the same, and that is the default for R. It's the same as having a kitchen. I guess this will be a stove. In Spanish, kitchen and stove mean the same thing. So, okay, so this will be a stove with one burner, right? If you are using this burner, you cannot use it by any other thing, right? If you are using your R session for maybe querying some database and this query will take 5 minutes, that same R session cannot be used for anything else until you finish that query, right? So this is the same idea here. But remember, when we are talking about R sessions, the R session exists, runs in your CPU. So a lot of times, I mean, maybe it's the norm even now that CPUs will have several cores available, even several threads available. Uh, so there should be a way to leverage this potential of your CPU in R, and it is. All right. So this is the concept of asynchronous programming, which means that tasks can run independently, right? Uh, and think of each burner of your stove as a core of your CPU, meaning that if you're using one core of your CPU, you should be free to use a different core for a different tasks, right? So while, let's say, if you're frying chicken on one stove, maybe you can cook rice on the other one. And you don't need for the chicken to be finished frying to start cooking a different thing on the other burner, right? This is the same idea applied to CPU cores. So hopefully that makes sense. But again, same following the kitchen analogy, if you're using more burners in your stove, it is also easier to burn your food because your attention will be divided, right? Same thing happens with the CPU. It makes asynchronous programming will make your program a little bit harder to debug. Errors will occur somewhere else, so you will need a way to deal with errors in a smart way. You might have for example, I'm listing here some possible complications. The code will for sure become harder to understand, and you will see in a minute. You will need to get familiar with how the code will look like. If you are using maybe these different processes for similar tasks. Maybe you were not careful enough, and they are writing to the same file, right? Maybe you are processing data from one region in one process, and you are doing for another region in a different process. But in your program, you specify the output file to be the same location. So even though you are running two processes, you are processing two different pieces of data, you will have the output on the same location. So the results will be overwritten. You know, whichever finish last will be the one holding the results. And maybe you don't want that, right? But it is a little bit harder to detect. Maybe you include some circular logic. Process A needs to wait for process B, which itself needs to wait for process A. And these processes are not aware that they are working on the same thing. So if the circular, I mean, your program will never end. It will just be using your CPU doing nothing because of this circular logic, right? It's difficult to debug, more difficult to debug because error occurs elsewhere. And of course, just the same as when you are using multiple burners, you will have higher energy consumption because each core of your CPU will require electricity, will require some voltage. High energy consumption will also mean that temperature of your CPU will be higher. So you need to take care of that. Be careful with how you are using the CPU, right? But of course, not everything is wrong with this. Benefits are that long operations don't block other operations, right? You can have one main task that takes a long time, but if in the meantime you want to have some tasks that are faster than that, you don't need to wait for the slow task to finish, right? You can start using your CPU for different things at the same time. So another thing important is flexibility, because if you are maybe waiting on some query from your database, or you are requesting something from an API, maybe the connection, the API server of the database server has some resource constraints and it became slower. And you were not anticipating this. This is something that you sometimes don't anticipate, right? But since your app is using, is using asynchronous programming, you will have other CPUs, other cores, other sessions available for you to use. If there was an unexpected delay on some of your calls, right? This also means that the application remains responsive. It will not hang. Right now, if you are using classic Shiny apps, when you are doing something slow, you cannot do anything else, right? It's like your application hangs in a block the status until it finishes computations. Something very interesting is that asynchronous programming is also efficient use of resources, because if you are acquiring a CPU with 8 cores, you paid for 8 cores, why will not you be entitled to use your 8 cores, right? You bought it for some reason, and you were expecting to use the 8 cores. It's the same as if you buy a truck and you only use it to carry your bag, it doesn't make sense to buy a truck only to carry your bag. It is efficient if you start carrying a heavy weight in your truck, right? This is the same concept here. And basically, this means scalability to a whole different level, okay? So let's jump into the code, because otherwise we will never reach the code. You do need some prerequisites, which is a CPU with multiple cores or threads. You will need some extra packages such as promises, future, and Shiny. If you want to use this extended task, you will need at least this version of Shiny. All right. It's not mandatory to use extended tasks. You can just use future promise, which I believe comes from the promises package, that will give you an easy way to implement async functionality. So the initial setup whether you use extended task or not, is to add these 3 lines to your application. You will add a call to the future package, which exports this function and also this function. And then you will need a call to the promises package, which will expose future promise that we will use later. And basically, this is doing what this does is telling Shiny to set up several background processes that will be ready to receive computations on demand when you request it. So if you want to use extended tasks, there is a really nice article here. I believe this is this one right here. I highly encourage you to read it. It's very nice, easy to understand. And I do what I provide here is basically same explanation with different data. Okay, so the starting point here is we can use a different action button here, which right now we are using the classic Shiny action button, but we can use a different one that comes from the bslib package that is called input task button. This, as you can see, is almost a drop-in replacement for the Shiny action button. You need to specify ID in a different way. It's not input ID, it's just ID. But other than that, it's the same thing. If you don't use future or promises here, if you don't use async, it will behave the same as the action button. All right. On the server side, what you will need to do is right now focus on this reactive value. This is the last optimizations that we implemented. We have the bind cache, we have the bind event, and we have the reactive here. Okay, we have everything here, remember. But so when we implement extended task, we do extended task because we want non-blocking async operations, right? So again, I encourage you to read this article to understand why we are calling them non-blocking operations, because just future promise is blocking, all right? But okay, so basically, how does it work? Okay, this is the whole implementation. I will go step by step. First thing is in the server, you need to create an extended task object. Okay, you can see here we are creating a new object, which is called filter task, which is a call to the extended task functionality, an instance of this class. And this basically will wrap a function. And in this function, we will need to provide some values. For this function, some parameters, right? Have in mind that this function will be called on another process, will not be called in the process where your R application is running. So anything you loaded for your R application will not be available here. So you need to make it available through this function. This function will also, as you can see, it is encapsulating the logic, the reactive logic that we had before. But instead of using the inputs directly here, we are using the parameters we are setting here in the function definition. And this reactive logic will need to be wrapped in this call to future promise, which is the actual thing that says R to run this on a different process, right? So this is the actual async implementation. And also have in mind that we have this bind task button, right? Okay, so next step after you have all the extended task logic is to bind to a task button, which is really easy to do. You, instead of having this bind event functionality that you had before, you will also add this bind task button to extended task. And instead of binding the event to a reactive, you will not bind it to an observer. You need to do this because this option will not run, I mean, you want to trigger this computation as a side effect instead of as expecting a return value, which are reactives. Okay, I understand might be harder this might be hard to understand, but please let's finish with this. Last thing you need to do is to invoke the task with this method from extended task. So remember, you created this task here. So the side effect that you want to trigger is invoking this task. So we have the data here, which is the whole data. We have the region, which will be mapped to the input region, and we have the input age. So this invoke will run with the same parameters you put to this function in the extended task. And lastly, the returning to reactivity logic. Now our filtered value that we had before, that was just a plain reactive, is now a reactive, but based on the results that we get from the filtered task. So the behavior from the user perspective will be exactly the same. They will have a button, but in the Shiny process, what will happen is instead of doing the computation of the main Shiny session, it will delegate the computation to the other session. So your app will not be blocked, and the user will be if you have several users, they will be able to use the same your main our Shiny app without being blocked by any other user's actions, right? So again, here you can see that render DT is the same as before. It's just a call to the filter value, which is again is a classic Shiny reactive. However, we did lose the cache here. This is because extended task right now is not fully compatible with the bind cache function. At least it wasn't the case when I prepared the material. I don't know if it has changed right now. But there is, and this is the whole implementation, and I would like to show you an easy way for you to have caching while using extended task. You will find this in the script directory. You have the app fast, which includes every optimization we covered in this session, and this is basically wrapping the future promise, another wrapper, and you will wrap this in this memoize function, which is like actually the backend that bind cache will be using. You will need to specify that the cache level will be the same as the cache as the default cache level you are using for your application. All right. So with this, you will have extended task, a non-blocking functionality, and also caching for your extended task. So yeah, I mean, this is fairly complex, I understand. But basically, it is how it works. And if you go to this application, this deployment, you will find the same app fast that I showed you recently is the same thing that is deployed here. To be honest, we are still more than 500 users. I don't think it will hold for 500 users, but I mean, give it a try. This is implementing every optimization that we are thinking, and it's also reading the whole data set, right? Because up until this point, we were only using a sample of 5,000 rows, but in that application, we are actually using the whole data set. So if the deployment is not working, please try it locally. I'm sure you will notice all the improvements that we were talking about. Okay, I think we did run out of time. I don't know if we will have time for more questions, but either way, I'm very thankful for you to be here. Maybe at some point I will, make a YouTube video with all the things I didn't cover here because we had some interesting topics to cover, but either way, I hope you enjoyed it. I hope it was useful for you, and I will be taking a look at the questions you had in the chat, and we'll try to answer every one of those. Okay, sorry, I'm back. I was just told that we have some extra time for questions, so I will not go to the rest of the material, but I will try to answer hopefully all the questions that we have for the session that were left unanswered. Okay, so we have. I'm sorry for those who already left, but hopefully this will be useful still for all of you that are still here. I will change the screen I'm using right now. Okay, Ramat Dadash is asking which package should I use to load hundreds of SAS files at a time. I'm not sure. I believe there is a Haven package that will support. It supports different formats, but other than that, I'm not really sure. I do recommend you to migrate to databases which will offer better functionality for reading data. Okay, we have another question from Miguel Ercel. What about the Polars package for fast data reading and data wrangling? I haven't used it. I haven't used this package. I understand there is also a Python implementation for this. If it's good for you, that is okay. I encourage you to do some benchmarks and try. Yes, I mean whatever is better for you. We have a question from Salome Whitber. What are the benefits and how does it improve the processes for Polar? I believe this question was not directed to me. Jeremy Wingate asks any profiling resources for positrons versus RStudio in a Rhino app or Shiny, or is Shiny TikTok simpler for that? I'm not aware of how well. I mean, okay, I guess I will share my screen. Okay, but when we were talking about profiling, we do have this. I mean, even if you don't have RStudio, I mean, you are using another IDE, you can still use the profiler like this. So instead of doing So I actually have never tried this, but I believe it should work. Right, this okay. So I believe if you do this, right, you should get the same result. I mean, until you stop the application and stop the profiler, you will get the same output as you will get for as in RStudio. Maybe you will need to do something like maybe you will need to give it a name to save the results of your profiling. I mean, ProfBiz is not tied to RStudio. It's just RStudio provides a functionality to have the results in a visual way. But yeah, you can use ProfBiz without RStudio. Okay, optimization Shiny. What's the difference between explicitly defining reactive dependencies using rec versus using bind event to define the reactive dependencies? Okay, so I understand what you mean, but rec, you mean this this right here, right? The difference between this and bind event. Basically, bind, as if you see here, bind event is not really concerned about the inputs we are using here. So you will, if you want to use rec here, it might be more useful for the actual reactives that you are using in your logic. But I mean, you don't really need this input compute to be part of your reactive logic. And to be honest, I find it easier. Maybe this is just subjective, but I find it easier to have only the really reactive logic inside my reactive expression here. Uh, I I think rec is something different. I think it was the only way to do things some years ago, but now we have some better interfaces. But I'm not really sure how to answer that, to be honest. Okay, so close glancer, is it cache on the server side, right? Yes, the cache happens in the server side. Joseph Orton, can you bind event to another reactive event? Yes, you for sure can. For example, you can do something like this. All right, filter. Maybe you were using a different reactive here, at some point of your code, and you can for sure use a reactive that was triggered by a bind event function to use it as a bind event input on itself. Yes, you can totally do that. All right, should we cache the data or should we cache the render results like plots and tables? It will depend on you, to be honest. Sometimes it will make more sense to cache the actual render, the actual renders, right? I mean, feel free to try different things. Just make sure, be sure that if you are using something like this, uh, so bind cache, you will expect it to work something like this, right? The key will be this reactive. However, if this data is big, if the data that you want to use as the key of the cache is big, it will not be as performant as you want it to be, because this whole data will need to be processed to be converted into a cache key, and that process is called hashing data. If this value here is big enough, it will actually slow down things. So it might not be worth it if you are using just an intermediate value here. So yeah, try different things, and again, do some profiling and benchmarking. All right. Okay, Salome is asking, is bind event faster than using event reactive or just simpler from the syntax? Event reactive is actually wrapping bind event. So let's say, I might be wrong, but okay, okay. So the important part here is this bind event, right? As you can see, event reactive is actually wrapping the bind event, and here is the reactive, right? So bind event might be uh, faster, but by a really tiny amount, but because you will be using it directly. Okay. What else? Tatiana is asking, is bind cache tied to the session user of all instances running at the same time? It will depend on your, sorry, where is it? It will depend on how you set up the level of the cache. You can see here, by default, it will use the same cache for every session, but you can tie the cache to a specific session, and yeah, it will be just for each user. Okay, Yi Yang is asking how cache is handled for bind cache after 200 megabytes is reached. Okay, this is an interesting question, because bind cache will use something, I don't remember the exact name of the algorithm, but basically it will remove the first element that you cache. Let's say if your cache, if every element of your cache is 40 megabytes, you will only be able to hold 5 elements, right? So if you need a sixth element, it will remove the first one, but it basically will be like the first in is the first out, right? Okay. Another question from Tess Hartog. What about if you're using leaflet to create maps, or is that a completely different topic? I would I would think that leaflet is also using something like we do for Plotly or DT, right? It will hold the recipe for your map, and then it will render in the browser. I'm not too sure about this. I believe that is what leaflet does. About server-side processing, we have, if you are plotting Plotly HTML files already created, okay, can you use Plotly output or render Plotly instead of using something like a render UI or using an iframe? Uh, I guess you will do something like render UI, but I will encourage you to take a look at the Plotly documentation. I mean, this is not in the scope of the workshop. Okay, Klaus Glanzer, we are reaching the section about async. Okay, basically async is server-side multi-threading. I believe basically, yeah, yeah, this is a way of understanding it, but let's be careful with the threading part of this understanding, because I will not be very sure that it is using actual what we call threads or logical processors, right? But I mean, as a concept, as a high level, yes, it will be basically the same thing. We have question from Lihai Song. Are there any efficiency difference between graph created using Plotly directly and convert graph to Plotly using ggplotly? Yes, I will say it is, but it should be tiny. It should be a tiny difference, where Yes, it will be faster to create the plots directly in Plotly syntax than to translate. But basically, because you will, when you create in ggplot syntax and then translate, you add this translation step, right? If you are using Plotly directly, you are not adding a translation step. So this is the thing that you are saving. It's only the translation step. Question from Thomas. Can you take advantage of async processing on a single-threaded open source Shiny server? I don't think so. You will need several cores, several ways of several threads to be able to take advantage of that. Question from Libby. Should I use plan multisession in my main app file, or if one of my modules is really slow, can I just use in that module file? I recommend it to set it for the whole app, but for it to be actually run asynchronously, you do need to use the future promise to wrap your expression in future promise. So anything you don't wrap in future promise will run in the main app. So yeah, you could have the plan multisession in the main file, but the future promise only for the slow part. Yeah, that is totally possible. Question from Roman Selmayer. What is the difference between future plus future promises to Mirai? Mirai is a kind of a new package for async processing, parallelization actually. I'm not totally sure, to be honest. I understand Mirai is I don't have to. I don't want to give you a wrong answer here. I encourage you to look at the Mirai documentation, but it claims to be true parallelism instead of whatever future is doing. I understand this is the main difference, and we will have a talk from the Mirai author here, Charlie Gao. I believe it's Friday, so if you want to hear from the man itself, please join the talk from Charlie Gao. He's called the author of Mirai. Okay, two last questions. Nina Otopal, we have a complex Shiny Golem app deployed with Docker. We have interactivity in sidebar for filtering, but also interactivity in the tables, which is even connected to a leaflet map. We have multiple users using this app at the same time, and we keep having RAM problems. Even if we set a restart in Docker Compose, the app doesn't restart if it just gets really slow when the RAM is reaching 100%. Is there a way to reset RAM inside the Shiny? RM and GC doesn't really help. I mean, this is a hard question. We will need to take a look at the actual code you are using for this. I mean, you have my contact in the slides. There is a slide about my contact in my GitHub profile. You can find my email. You can reach me through email or LinkedIn. I mean, those are the ways I could help you, but I don't think I can answer right here. Angelo has a question: why the need of both bind task button and bind events, both pointing to the same input? Okay, basically because what the first bind task button is doing is setting the behavior for the action button to show this loading. Is like a loading message, right? But the actual reactivity that will be triggered by the button happens with the bind event. So it's basically, I think, a matter of how the button will be styled, and nothing else. All right. I guess those were all the questions. Again, thank you for being here. And you can reach out to me on LinkedIn, on GitHub, on email. So I'll be seeing you there. And thank you, Sasha, for the help. Thank you, Marcin, at the backstage. So see you on the other talks. Bye.